So yeah, I'm really glad that they asked me to come as well. What I want to talk about is joint work with Ruth Charney, trying to do an outer space for right-angled Artin groups. So I'm not assuming that everybody knows what these are, although I know half of the people in this room are actually experts, but I'm going to start from the beginning. So right-angled Artin groups, what are these? It's very simple groups. You just, they're finitely generated groups, and some of the generators commute, and that's the whole presentation for the group. So in order to describe this, you usually draw a graph, a simplicial graph, meaning there's no loops or multiple edges. The vertices correspond to the generators, and you draw an edge between two generators if the generators commute, and that completely describes your group. So here's some examples. On the left, there's a graph with 5 generators and all possible edges. So that's the free abelian group on 5 generators. On the right, there's a group with 5 generators and no edges. So 5 generators, none of whom commute. So that's the free group.
Could the light be turned off?
Ah, yeah. I could try. Is this lights? Is that better? Right, here we have two connected components. We've got a free abelian group on top and a free abelian group on bottom. And so you get the free product of those two. On the left, you have a free group on top and a free group on the bottom, and they commute with each other, so you get a direct product. And in the middle, you have a graph, and you have a group. So these groups are really easy to describe, and they look extremely simple, but it turns out that they're really interesting. They have very interesting subgroups in particular. Long time ago, Stallings and Bieri used them to find subgroups with very strong finiteness properties in just small dimensions, and bad finiteness properties in large dimensions. Bestvina and Vedi showed that they've got subgroups which satisfy homological finiteness conditions, but not the analogous geometric finiteness conditions, which you might have thought were the same thing. Croak and Kleiner used them to find groups, found subgroups which act properly and co-compactly on 2 different cat-0 spaces with non-homeomorphic boundaries. So this makes them very different from hyperbolic groups. For instance, cat-0 groups are very different from hyperbolic groups, where the boundary is a well-defined invariant. And then, of course, there's the recent work of Ian Agel, who shows that the fundamental groups of hyperbolic 3 manifolds are virtually subgroups of rags. And that was one ingredient in his solutions to the Thurston conjectures. So rags have been in the news a lot. They've been around in geometric group theory for a long time. The classical ones, the ones you start with on either end, like z to the 5th, has a very interesting automorphism group, namely GL5z, GLNZ in general. And free groups have really interesting automorphism groups, those the automorphisms of free groups. I'll be mostly concerned with the outer automorphism groups. So the question is, supposing you have a random rag, what does its outer automorphism group look like? Now, I should say that there is a theorem that says the, quote, random rag has a finite outer automorphism group. But this is a little sort of a misleading theorem. It means that as the number of vertices in the graphs goes to infinity, the percentage of graphs with infinite outer automorphism groups goes to 0. However, if you know anything about the number of graphs on n vertices, it grows very, very fast. And in fact, the number of graphs with interesting, well, at least infinite automorphism groups also goes very fast. It's just that the number of graphs grows faster. So, yeah. So there are lots and lots of interesting outer automorphism groups. So the problem is to study these groups for an arbitrary graph. And there's kind of 2 flavors of this problem. First of all, GLNZ and out of FN share a lot of basic properties. So which of these are properties of all outer automorphism groups of rags and which are specific to these groups? And then also, but also they're very different in many ways. Like out of FN doesn't have any solvable subgroups except for abelian ones. And GLNZ obviously has, well, it's got all the polycyclic subgroups in it. So how does the shape of the graph affect the group of outer automorphisms? So I want to use geometric methods to study these groups, so I need a space with a useful action of the outer automorphism group. But before I do that, I should point out that there has been a fair amount of work recently done on out of A gamma. Servatius conjectured a group of generators, and Laurent proved that they were generators in 1995. So it's a finitely generated group always, and in fact, it's always also finitely related. Ruth Charney and I did that for a lot of groups, and Day did that for all of them. The outer automorphism group is residually finite. Both Charney and I and Manassian proved that. We studied the solvable subgroups in rags, and we came up with a lot of information about that, and Day came up with even more information. So there has been a lot of work, but you know, all of this uses kind of inductive methods and algebraic methods, and you'd really like to see a space if you do geometric group theory. So Ruth and I tried to do this once before. In 2008, we invented a space. It's a nice space, but it only works for two-dimensional rags, which means that there's no triangles in the graph. Right, so what this current push now is to do something for all rags. And it's something different than what we did then. So right, you want to study automorphisms. So the two models for studying automorphism groups are, well, we've got our two classical groups, GLNZ, which acts on its symmetric space. And out of FN acts on a space which is called outer space. And the useful features of these spaces is that they're contractible. The actions are proper. So in particular, that means if you're interested in invariants like homology and cohomology, you can compute them by computing the cohomology of the quotient spaces. For instance, the fact that these spaces are finite dimensional implies that the cohomological dimension of the group is the virtual cohomological dimension is finite. These spaces have co-compact equivariant deformation retracts. So in particular, that means that the cohomology of the group is the cohomology of this compact space, so it's finitely generated. They also have nice spaces at infinity. This is asymptotic group theory, so I should say something about infinity. So there's the fact that they've got a nice compactification. You can figure out what the cohomology at infinity of the boundary, it gives you a duality theorem between homology and cohomology. So those are the kind of features we would like in a space for studying automorphism groups of rags. Whoops. And we're done. Yeah, this happened a couple times last night, too. But yeah, last night it kept coming back. Let's try this. All right, so we start with the symmetric space for GLNZ. That's the classical space, SLN mod SON. Space of cosets, you can think of that. or it's got a lot of other descriptions which turn out to be useful in various contexts. For instance, you can think of it as a space of positive definite quadratic forms. It's a nice description because it makes it really easy to prove that this space is contractible. Because if you have, you can draw the straight line between two positive definite quadratic forms. It consists all of positive definite quadratic forms. You get a positive cone. You can also think of it as a space of marked lattices in R to the n, modulo rotation and homothety. Or you can think of it as a space of marked flat tori. So let me show you how this goes. You start out with a coset SON times a matrix A. How do you get a positive definite quadratic form out of that? Well, you take A transposed by A. It doesn't matter which element of the coset you take, because O is orthogonal. Or to think of it as a lattice, you take this matrix A and think of it as a map from Z to the n into R to the n. And we're doing it modulo rotation and homothety because we're looking at special orthogonal group over there, and we're modding out by rotations. I think of it as a space of flat tori. This map from Z to the n into the R to the n, well, it's an element of SLN, GLN Z, so it sends Z to the n to itself, so it induces a map on the quotient torus, and it goes into Rn modulo the image of the map. So this is a torus with a non-standard structure, and this is the standard torus. And how does the group act? Well, it acts on the right in all these pictures. So that's easy. You just multiply the matrix by a group. Here you conjugate your quadratic form by your group element. Here you precompose this map by a map Z to the n to Z to the n. And here again you precompose. You realize this map by a map of a torus and compose. So that's four different ways to think of this symmetric space. This is the one I want to focus on. So let me just repeat what you do. You're thinking of this as a space of marked flat tori. So you fix a model torus, which is the R to the n mod Z to the n. It's got fundamental group Z to the n. And then a point in your space is a marked flat torus. So that's a flat torus X, that's over here, with a homeomorphism from your standard torus to your strange torus to your flat torus. And and you do that up to isotopy. And a group acts by changing the marking. A group element GLNZ acts by changing the marking. So if you'll accept this definition of a symmetric space, then I can tell you what outer space is in one slide. So we're going to do exactly the same. Oh yeah, sorry. One comment here, you can replace homeomorphism by homeomorphism up to isotopy by homotopy equivalence up to homotopy if you like. Okay, now we can do outer space. Okay, so how do we get from this to outer space? Well, it's going to be a space of marked metric graphs. So the model, instead of a torus, is a rose. It's a graph with one vertex and edges. A marked metric graph is going to be a metric graph, together with a homotopy equivalence from our standard rows to the metric graph. Instead of a flat torus, we have a metric graph. And how does the group act? Well, any automorphism of the free group can be modeled by a homotopy equivalence of the rows, and then you just compose, and you get a new marked graph. So that's outer space. So we have two spaces with the same type of description. For n equals 2, they're very closely related, these spaces. So let's do out of A gamma for two vertex graphs. So there's only two vertex graphs. There's that one and that one. The one on the left is the free group, and the one on the right is the free abelian group. So we actually already know about these. fact is that the map, there's a natural map from out of F2 to GL2Z, and that's an isomorphism. So these groups are very closely related. I mean, they're isomorphic groups, and in fact, the symmetric space is actually homeomorphic to at least reduced outer space. So they're the same space, different groups, the same space. I mean, the same groups, sorry, the same space. So yeah, that's what it looks like. I've drawn it as a space of marked metric graphs. You should think of, whoops, it disappeared already. Wasn't supposed to disappear that fast. Okay. So you should think of those graphs as points in that space as those graphs with various edge lengths on the graphs. Now it can disappear. We'll see it again. So we've got two different descriptions of the same space. One is a space of marked flat tori, and one is a space of marked metric graphs. And it turns out it's useful to understand the correspondence between these two descriptions, because that'll help us to construct an outer space for an arbitrary right-angled Artin group. So let's start with this one. GL2Z is generated by inversions. I don't actually need all those generators. These are transvections. I can multiply A by AB. If I think of this in the standard matrix terms, this is just an elementary matrix. And let's think of the model of this as a space of lattices. So how does this group element act on a lattice? Let's take the standard lattice and apply 1, 0, 1, 1 to it. And there it is. That's what happened. So you can't really see what happened, but the problem is that we weren't thinking of a marked lattice, right? So marked lattices come with an isomorphism of z squared in there. So that sends 1, 0 someplace and 0, 1 someplace. And now if I act by 1, 0, 1, 1, I can see that it's a different marked lattice, the same lattice. However, the set of lattices you get this way by acting by elements of SLNZ is just a discrete set. And we want a space of lattices. So in order to get from that one to that one, you need a path. And you do the thing you would naturally think of doing is you just shear the lattice. Okay, that gives you a path of lattices, of marked lattices. So I'm going to do this again. I'm going to keep track of where I started with the little black box. I'm short on time. I'm not going to repeat. Now I told you I didn't really want you to think of this as a space of lattices. I wanted you to think of it as spaces of marked tori. So let's look at the quotient of this, of the blue spot, of the blue guy by the lattice, and also keep track of the black box. So if I go a little ways, notice that the vertical black line no longer matches up to itself when I glue the blue parallelogram together to make a torus. So as I go along my path, that black line up there does a full twist. It started out with a rose, and became a trivalent graph, and then closed up again to a rose. So that's the picture for the torus. Now, what about the picture for a free group? This is supposed to be a space of marked tori, of marked graphs. Well, a free group, F2, is just the fundamental group of a punctured torus. So I puncture my torus and let it all shrink back to a spine, which is just this red graph. Just leave the graph there. That's got its edges. That's a rose. The little dotted lines mean you connect you identify those edges. And what happens as you go along the path is this rose becomes a trivalent graph. And then by the time you get over here, remember the right-hand side gets glued up to the left-hand side, so you have a rose again. And this is just to, if you keep track of what happened to the vertical line in this thing, it got stretched around the horizontal line. So that one generator got wrapped around the other generator. This is what Gilbert was calling sliding. Okay, so this tells us, this is in the space of graphs. We had to go through graphs that weren't like the rows. They weren't like our model space. So we had to consider other homeomorphism types other than our model. For this, we had to consider, all of our spaces were homeomorphic to our model, but they had different metrics on them. So in general, we're going to have to both change metrics and change the model to get a space for a general A gamma. But in general, we want it to be the same sort of thing. We want it to be a space of marked metric spaces. So we're going to need some model space whose fundamental group is A gamma. A point is going to be some metric space and a homotopy equivalence to the model space, like that. And a point should act by modeling an automorphism of A gamma and composing. So we now are left with the question of what model spaces should we use? What other spaces X do we need? What homeomorphism types? And what metrics do we need on these spaces? Okay, so here's the model spaces. You start with a rag. You have something called the Salvetti complex. So this is a space with it's a space made out of cubes. It's got one zero cell, and it's got a K torus, which is a cube glued up, for every K clique in your graph. So let me do some examples. There's a graph. So I'm supposed to have one zero cell, and I'm supposed to have one torus for each one clique. One cliques are the biggest cliques I have in this graph. So I need 3 one cliques, A, B, and C, and I need to glue them onto my zero cell. So there, they're glued on. Here, if I have 3 points and an edge, then I have to do the same thing, but I also have to add a 2-dimensional cube for the AB torus. So yeah, I glue that on and get a torus. Okay. If I have a complete graph, then I have to start with A, B, and C and glue on 3 tori and glue on actually a 3-dimensional cube. And you're just waiting to see what I'm going to do here, right? Yeah, sorry, nothing else. A, B, and C. This is one more example. So this is the only example. Yeah, I'm going to follow this example through the rest of the talk. I've got 3 vertices, so that corresponds to the 3 one-dimensional cubes, and 2 tori, the AC torus and the BC torus, two squares glued on. Okay? Right, so what homeomorphism types of spaces am I going to need? Well, so I want a point of outer space to be a pair, where this is a metric space and that's a homotopy equivalence. I'll certainly want to include some spaces that are homeomorphic to my model space, but what else do I need? So in order to understand what else you need, I want to think about some actual automorphisms of A gammas, what they look like. So here's a basic fact about out of A gamma. Well, you know generators for GLNZ, those are the elementary matrices, plus an inversion, I guess. And you know generators for out of Fn, those are transvections, right and left transvections and an inversion. You don't actually need all those, but those are fine. So what about arbitrary A gamma? Well, all you have to do, there's not many relations in this group. You know, there's just commuting. So as long as you preserve the fact that things commute, you're happy. So in particular, if you invert a generator, you haven't changed any commutation relations, you still have an automorphism. If you do a graph automorphism, that sends things that commute to things that commute. So you have an automorphism of your group. It's not true that every transvection gives an automorphism, however. For instance, in this example, if I try to multiply C by A, I can't do that because B commutes with C, but A doesn't. So it didn't preserve the fact that C commutes with the image of C doesn't commute with the image of B, even though C commuted with B. So the thing that's wrong here is that, things that commute with, if I want to do a transvection, then everything that commutes with C has to also commute with A. Or in terms of the graph that says that the link of C has to be contained in the star of A. So it turns out that that's really all you need. And this is Lorenz's set of generators for aut of A gamma. There's graph automorphisms and inversions. And there's things that I'm calling twists, folds, and partial conjugations. Graph automorphisms are self-explanatory, so are inversions. What's a twist? That's a transvection. I'm calling it a twist if the x and y commute. And in terms of the graph, that means the star of x is contained in the star of y. I'm calling a transvection a fold if x and y don't commute, and that's governed by the link of x being in the link of y in terms of the graph. And then there's something called a partial conjugation. If you've got a vertex and its star cuts the graph into two pieces, let me see. I could conjugate everything over here by x and nothing over here by b, and that would still preserve all commuting relations, because the guys in here can't tell whether they've been conjugated or not, because they all commute. So that's a type of automorphism you don't have in, you don't really have in GLNZ or so much in out of FN. Okay, so those generate. So in our example, what do we have? What are the graph automorphisms? You can switch A and B. You can invert A. You can invert C. You have to put those both in because you can't permute A and C. What are the twists? You can multiply A by C. Can't multiply C by A, but you can multiply A by C. Folds, you can multiply A by B or B by A. And there aren't any partial conjugations because this example is too simple. So those are our generators. So why did I call these twists and folds? So remember what we did for the lattice. We had this point, and we applied a group element, and we got another point, and we needed a path between them. So we needed to shear our shear our lattice. So supposing I have this point and I apply the graph automorphism switching A and B, I can realize it without moving this graph, this complex at all. I just get the same complex back again just by an isometry or homomorphism of the complex. Same thing for A goes to A inverse and C goes to C inverse. But if I want to do A goes to A times C, then what do? I twist A around C. Okay, so this is exactly the picture we saw in the lattice, right? We have something twisting around. So that's why it's called a twist, because it twists. What about this one? If I want to multiply A by B, well, I have to start with the AB rows, and the idea is to kind of fold the yellow torus around the purple torus. And that will go through some intermediate stages. Let me do that a couple times. I don't know, it goes by sort of fast. Okay, so you fold A around B. And somewhere in the middle, you've got it partly folded around. So in order to do that, you have to change the homeomorphism type of your space. Right. So here's my proposal for what an outer space should be. So a point should be a pair where X is some kind of a cube complex which collapses to your standard Salvetti. So if you just collapse this part down to a circle, it collapses to the Salvetti. That should be a homotopy equivalence. And these guys should all have non-positively curved, should have a non-positively curved metric which restricts to a flat metric on each torus in the picture. Okay, let me, and the out of Fn should act by changing the marking. But I actually have to be a little bit more precise. This is what we had trouble with several years ago when we tried to do this. We weren't restricting the kinds of cube complexes we were looking at. And it turns out that you don't want to use any more than you need to. So what kinds of cube complexes am I interested in? Well, there's some basic cube complex definitions. These are supposed to be non-positively curved. So that means if I take a little sphere and intersect it with the link of a vertex, every time I see a triangle, it should be filled in. I'm not actually putting a metric on these yet, so that's a combinatorial condition, so I'm calling it NPC. And then you have to know about hyperplanes. Incidentally, these cube complexes don't look like the ones I was drawing but whenever anybody talks about cube complexes, they always draw cubes. My cubes had sides identified, right? They glued themselves up into tori, but you have to imagine that here. Okay, hyperplanes are things that go through the middle of cubes. There's 3 of them. And there's the notion of a hyperplane collapse, which takes a hyperplane and collapses it down to one of the sides. Okay, so here's the technical definition of the kind of cube complexes I want. I want an NPC cube complex. I want some sequence of hyperplane collapses to give me the Salvetti complex. I want all the hyperplanes to be non-separating, no 2 are parallel. And this is another technical condition. Let me just illustrate these on my example. I get from that to that by collapsing that blue hyperplane. The image of all the hyperplanes are non-separating. There's also one other hyperplane which is also non-separating. And the image of all those hyperplanes are hyperplanes over here, or else they're in the collapsed piece. So with all those definitions, I can now say exactly what kind of cube complexes I want. I want these things. I want gamma complexes. Right. And I want homotopy equivalences. So I now have a set of homeomorphism types and of marked homeomorphism types of objects. And they form a partially ordered set under hyperplane collapse. So yeah. So I can take the geometric realization of this partially ordered set and get a simplicial complex. If I do this for the free group, then a marked gamma complex is just a marked graph. And the geometric realization is the spine of outer space. So let me go back to my picture. So there was outer space. For each of these guys, I'm not thinking of the metrics, so I only get a single point for each graph, for each simplex in this picture. And then I go from one to another. The 2 of these points are joined by an edge if I can get one from another by collapsing something. So if I start at the middle graph, there's 3 directions to collapse because there's 3 edges to collapse. Okay, so that's, yeah. So if there aren't any twists and out of a gamma, then the geometric realization of this partially ordered set is connected. And in fact, it's a theorem. Oh, right, it's a theorem. but we're not getting there yet. I want to think about the subgroup where there aren't any twists. So that's just the subgroup generated by everything except the twists. Might be everything, it might be finite. But in any case, it's a subgroup, and here's the theorem that if you look at the connected component of this partially ordered set, of this simplicial complex that contains the identity from Salvetti complex to itself, then that's contractible. And this subgroup acts properly and co-compactly on it. So this is the kind of a space we wanted, but it's not for the whole group. It's just for this subgroup. If I have twists in my outer automorphism group, then I get a disjoint union of translates of this contractible thing. And, right. Yeah. I don't really have time to tell you how to prove this fact, this theorem. So I'm going to do something I hate. I'm going to flip through some slides really quick. I'm sorry for this. Nico Saberk isn't here, is he? He hates this, right? Okay, good. Yeah. So what I'm doing in these things that I'm going very quickly through is describing exactly what kinds of homeomorphism types I need in my space. So you saw that to get from, in my example, to get from one thing to another, I needed to go through a different homeomorphism type. And I needed to do that by kind of uncollapsing something, which I call blowing up. So this explains all the different ways you need to blow up in order to get an actual contractible space. Yeah. So you need things like that. You get this by blowing up this circle into a cylinder. Right. So all of this is explaining that. Right. But now I can get to this point. So we have a space. We kind of think of it as, yeah, it's a contractible piece of a space, and we have all these copies of it, but they're not joined together. And we would like to join them together in order to make a space on which the whole group acts. So for this, you should remember that you get all of outer space by adding metric information to the graphs. So we start with the spine, which is the geometric realization of this partially ordered set, and you add metric information, and you get the whole space. If you have twists, then that doesn't work. You don't get a contractible space. For instance, for z to the n, this the whole complex that I'm talking about, the connected component of the identity is exactly equal to the identity. So the k gamma is a point, which is contractible, but yeah, it's not very interesting. So this point corresponds to the torus made out of a square. If I change the side lengths of the square, I can get a slightly bigger space. I can get a one-dimensional space if I insist that the squares still have area 1. And if you know what this is, this corresponds to the Levy component of GLNR. And then if I look at the translates of this under GLNZ, I get the entire fairy graph. So the space I've got so far in this example is just the edges in the fairy graph. And I need to fill it in somehow. Okay, so how do you do that? Right, so we have a disconnected space. We have all those edges. They don't have their endpoints. So in order to get a connected space, you have to shear the metrics on the cubes. But you only need to shear metrics on cubes where there's a shear, where there's a transvection you can actually do. Okay, so yeah, so what kind of metrics can you get by shearing? Turns out you can describe exactly what metrics you can get. So shearing's governed by twists. And it turns out that when you map out of A gamma to GLNZ and you just look at the twists subgroup, then that map is injective on the twist subgroup. So you can see the twist subgroup as a subgroup of GLNZ. And in fact, what it looks like is a block upper triangular group. Diagonal blocks correspond to K cubes, which can be sheared in all directions. And that corresponds to sets of K vertices that all have the same star. And the space of metrics you get by shearing in these directions is homeomorphic to the real points of the image modded by the real points intersected with SON. So let me do the example here. Yeah, this is a theorem 80. It was a theorem 90 last summer, but it's not done yet. If I look at these metrics, and I also have to say what metrics I put on blow-ups. I think of the metrics on blow-ups. When I blow something up, I stick in a subcomplex, and I'm thinking of that as a rectilinear subcomplex. If I put those metrics on, then I get a space. And the claim is that that's contractible. Thought the proof was done last summer, and I think I gave talks saying that it was. It's done in lots of cases now, but it's not completely done yet. But I'm sure it's true. Anyway, so then this is I have a proposal for a space, which I've more or less described. And the claim is it's contractible. So let me just finish with my example. So that's a blow-up. Those are the only kinds of blow-ups I have, other than the Salvetti. And the twist subgroup, the only twists, I can multiply A by C or I can multiply B by C. So if I put A, B, and C in the right order and look at the image in GLNZ, I get, if I put C at the top and then A and then B, I get this subgroup of upper block upper triangular matrices. It actually has ones in the diagonal. This is a subgroup. It's isomorphic to R squared. And so I claim that the set of possible metrics I can put on this thing, I'm allowed to put on this thing, is R cross R. And how do I see this R cross R? Well, think of each of those guys as a right circular cylinder. And the metric is determined by the heights of the cylinders, their common radius, and the attaching maps to the two circles. Whoops. Yeah, so the attaching maps, you parameterize by how much they twist when they attach. They can twist, there's a whole real line's worth of twists for each of two cylinders. And that completely determines the flat metrics on this thing. That's all you can get by shearing. It looks like you can twist in 3 cylinders. But if you twist in 3 cylinders, you can always untwist one of the cylinders, and it's really only twists in 2 cylinders. So that's my example. I have a lot of questions. This is a space, and it's new, and there's millions of questions. I'm going to show the last one, because I'm out of time. I'm sorry, I misjudged the time here. There we go. Does out of A gamma always have finite asymptotic dimension? So Mladen first has to show us how to do out of Fn. When he's done, we can do this one. Okay, so that's all.
Are there any questions?
too.
All right, I guess. Oh, no, is there one?
What would be the next series of groups that you would like to consider and study the outer automorphism group?
Yeah. Well, I've been kind of obsessed for a long time with comparing out of Fn with GLNZ for various reasons. So I think I'm probably going to stick with this one for a while, because this kind of, I'm hoping they're kind of inductive arguments to get me from out of Fn to GLNZ and back by throwing edges out of graphs or inserting edges into graphs in clever ways and answering some of the questions I still have about out of Fn. So.
Any other questions?
If you add a graph in an edge in a rag, is there any map from the corresponding outer space that you have?
From the, no.
No?
No. I mean, no. I mean, it's like, think of the two, yeah. For the case of a graph with two vertices, yes. But it's not, yeah. I don't know, maybe there is. You could puncture the torus and kill the edge. Yeah, maybe. Interesting idea.
Any other questions? All right, let's thank the speaker again.